This one? Hello. Okay. All right. So I am now an amplified. Thank you. That was my husband. Okay. So I am Victoria Meadows. I've managed to figure out how to use a mic, and I am the director of the UW Astrobiology graduate program. So I would like to welcome everybody to the final lecture in a four-part series to celebrate the 25th anniversary of our graduate program. So astrobiology is a massively interdisciplinary science that is about the study of life in the universe, its origins, evolution, and future. So astrobiology helps us understand where alien life might be beyond the Earth and how we should go about looking for it. So it gives me a great deal of pleasure to introduce tonight's speaker, who is Dr. Aomawa Shields. She is the Clare Boothe Luce Associate Professor in the Department of Physics and Astronomy at the University of California, Irvine, which is a bit of a mouthful, where she leads research in exoplanet habitability. She is also a fellow of the California Academy of Sciences and a 2015 TED Fellow. She and I first met actually when we both worked on the Spitzer Space Telescope user support team, which Omo reminds me was back in about 2005. So that's, yeah, we can't believe it either. So it's been about 20 years now. So Aomawa is an alumna of the UW Astrobiology program. She graduated in 2014, and somewhat unusually, she also holds a Master in Fine Arts in Acting from UCLA. This is a fantastic combination, and you will get to benefit from that today. She has received many awards, and perhaps the most notable being the 2025 recipient of the Presidential Early Career Award for Scientists and Engineers, which was awarded to her by Joe Biden. I guess back in January. All right. Okay. And she's also the founder and director of the Rising Star Girls program, which encourages girls of all colors and backgrounds to learn about, explore, and discover the universe using theater, writing, and visual art. So Dr. Shields also uses her theater background to communicate science to the public in engaging and innovative ways. And again, you get to see that tonight. She's also written a memoir entitled Life on Other Planets, a memoir of finding my place in the universe. So if you want to learn more, there's a book. So tonight, Oma will share some of her scientific expertise on planetary habitability, as well as her personal story on becoming an astrobiologist. So please join me in welcoming Professor Shields and her presentation on the climatic effects of the UW Astrobiology program on the habitability of my environment.
Good evening. Can you all hear me okay? Okay, good. Thank you, Vicki, for that wonderful introduction. It's my honor to be here and to be able to close out this incredible series celebrating 25 years of the astrobiology program here at the University of Washington. I'm excited to tell you a lot tonight. Before I launch into it, I want to cover the most important part of this talk. If you remember nothing else, let's remember how to pronounce my name. Vicki has it down. She's had a lot of time, although I think she had it down pretty much within the first week of meeting me. But there is a learning curve, and so I wanted to give you the fast track. It's pronounced Aomawa. Emphasis is on the O, and I thought for an interactive portion of the program, we could all say my name together. So on the count of 3, 1, 2, 3. Aomawa. That's literally music to my ears. And if you read the book, you'll know a lot more about that. It's a song, and it's more and more. So I'm also going to do something that you may never have had done in a talk that you've attended before. I hope you have, but it's probably unlikely. For those who'd like to, I'd like to do a collective practice, and this is secular, mindfulness-based meditation practice. So for those who'd like to, it's not required. No one's going to be kicked out if you don't participate. But if you'd like to, I invite you to close your eyes at this time. Or if you're not comfortable closing your eyes in a public setting such as this, you could maintain a soft gaze, perhaps keep your eyes at about a 45-degree angle towards the floor. And allow yourself to sink deeply into the surface beneath you and the surface behind you. do a quick body scan, starting at the top of your head and moving down through the face, allowing the space between the eyebrows to be soft and smooth, allowing the cheeks and the jaw to relax. You can even let your lower jaw drop open. Nobody's watching. Allow the shoulders to be soft. Belly soft. And invite any other areas that you may have been holding tension previously unconsciously to soften further. Take a full deep breath in through the nose and sigh it out through the mouth with any sound, allowing your body to soften even further. And again, in through the nose, sigh it out through the mouth, inviting any additional tension to relax and release with the exhale. And return to your natural breathing. And notice how the breath is like a wave. As you breathe in, belly rises, chest rises. And as you breathe out, belly falls, chest falls. Over and over. So tune into that wave-like nature of the breath for a few breaths. Just breathing. And I want to invite you to imagine that you have arrived at a new world, a new planet, and you're the first person to step foot on this world. Imagine that you exit the spacecraft and you know that there's air to breathe, that it's safe to remove your helmet. And as you do so, you open your eyes and your ears and you look around and you listen. What do you see? What do you hear? What does the landscape look like? What is the color of the sky? How many stars, how many suns are in the sky? Is it day or night? Do you see any signs of life there other than your own? If so, what does it look like? What is the landscape like? The topography? What are the temperatures? Do you feel wind on your skin?
Do you have any idea how to project this?
And allow any of that information to settle deeply in your body. for now, let's return to the room that we are all in here tonight on this planet. Let's take one more full, deep breath, perhaps the deepest breath we've taken all day so far. In through the nose, sigh out through the mouth. And when you're ready, you can open your eyes. Our planet orbits one single middle-aged star in a galaxy of hundreds of billions of stars. And this is a picture in a couple of ways of our galaxy. So often when we think about the Milky Way, which of course is our galaxy, we can think about this band, this swath of stars that many of us have had the fortune of being able to see on a dark night, perhaps in the desert. How many of you have seen this band? It's from somewhere in the world. Okay, great. And of course, when we say, oh, there's the Milky Way, well, we're in the Milky Way. So it's not that the Milky Way is out there and we're not in it, but we're looking towards the center of the Milky Way, towards the densest collection of stars. And that's why we see it as this thick, bright band. Although these dark lanes here, as we'll talk about a little bit later, doesn't mean there's nothing there. In fact, there's a lot there. This is an artist's concept of our galaxy, not a real photograph. Now, why do I know that? How can we be sure of that? Anyone have an idea? Yes. Has anyone ever done so? No. Yeah, absolutely right. Yeah, no spacecraft has ever left the boundaries of our galaxy yet. Voyager 1 was launched in 1977 to fly by Jupiter and Saturn, and it only just exited the boundaries of the solar system and entered interstellar space in 2012. And it's still taking data, but it has not come anywhere close to exiting our galaxy. So we know this is an artist's concept, but we have many pictures of other galaxies because we are outside of those. So here's what we're fairly certain our galaxy looks like. It's a spiral, and we are in this little bubble. So this, on a clear night in the darkest, like desert night sky, we might be able to see 6,000 stars with the naked eye. And those stars would be comprised within this tiny little bubble. There are more than 100 billion stars in the entire Milky Way galaxy. So given that there are over 100 billion stars in our galaxy, and there are more than 100 billion galaxies in the observable universe, that's a lot of stars, right? And I like to think about this when I think about this kind of picture, which is the Hubble Ultra Deep Field image. It's one of my favorite images. And it's every single point of light pretty much in this photo is not an individual star. It's an entire galaxy. There are about 10,000 galaxies in this image. And it was taken over total exposure time of 11.3 days. And it was taken over several composite photos put together, many. So this is what we're talking about. Sheer numbers alone, we have a lot of prospects for potentially habitable worlds in our galaxy, let alone universe. So we are living in a whole new universe now, where once it was believed that only our planet was the only planet that could sustain life and could ever host life. We now know that the universe holds an enormous number of stars, with almost every star having a planet around it. Therefore, we have a number of prospects for life through sheer numbers alone. And I like to think whenever I'm asked about the question, like, do you think that there's life elsewhere? I think about the movie Contact. Who's seen this movie? Okay, good. When I ask this question in my undergrad Life in the Universe class, almost no one raises their hand, because no one was born when the movie came out. It's a fantastic movie. It's an even better book. And in this movie, Eleanor Arroway, the astronomer, is asked about the prospects of life elsewhere. And she says this quote, I think that comes from her father, that if it's just us, it'd be an awful waste of space. And that's what I think too. I can't prove it, but I believe it. Of course, there is a difference. So now we know of over 5,000, and in fact, that number is now closer to 6,000 planets found around other stars. We call these planets extrasolar planets, or exoplanets for short, across a range of regimes. And of that number, we have a fair number of them that are potentially habitable, they're rocky, they're terrestrial. If they're rocky, then you could have an ocean sit on it, and we certainly know that oceans on our planet are teeming with life. So the overall goal is to turn an artist concept like this is of an exoplanet environment, or this one, again, another artist's concept of an actual exoplanet that was discovered, into hopefully a real photograph like this is, taken by Ansel Adams of the Tetons and Snake River in 1942. So again, we're hoping to go from this artist concept to this real photograph. We have a number of missions that have helped to increase these numbers of exoplanets that we've discovered. The Transiting Exoplanet Survey Satellite, TESS, is looking in the nearby solar neighborhood for planets. And that's really good because it means if we can find them close by, then it's much easier to follow up on these planets to look for signs of life. And of course, we have James Webb, which has brought us unprecedented data of a range of astronomical phenomena, including planets. And really hot off the presses, we have an exciting proposed discovery, I will say. It's under a lot of scrutiny right now, but a planet, K2-18b, has been reported to have a molecule in its atmosphere that on the Earth is associated with phytoplankton in our oceans. And so again, this discovery is being heavily scrutinized. But I think what's exciting about it, I enjoyed sharing this with the class I'm teaching right now, my undergrads, the Life and the Universe class, to tell them like what you're learning about right now is happening out in the world. Scientists are taking data. Scientists are arguing over that data. This is an area of active research, and we could find the answer to that question, are we alone, within your lifetime? We also have things going on, not just up in space, but on the ground. Huge telescopes, extremely large telescopes. They're actually technically called that, extremely large telescopes. And they are helping to find these planets and help hopefully characterize their atmospheres too. And all of this is kind of paving the way for what we hope will be a dedicated mission, something like the Habitable Worlds Observatory that we need to be able to definitively identify atmospheric constituents on a planet that show us unequivocally that there's life there. So, we're looking for that holy grail in the field of exoplanet research, the discovery of another habitable planet like the Earth that's capable of supporting and maintaining life over long time scales and perhaps currently hosting life. But as these numbers continue to increase, the numbers of exoplanets that have been discovered, we aren't going to be able to follow up on every single planet to look for signs of life in its atmosphere or on its surface. We need a way to prioritize those planets. And that's where my work comes in. I don't find the planets, but I can tell you what their climates are like and how likely they are to have environments conducive to the presence of life. I use climate models, and these are climate models that have been used for a while now to predict climate and weather patterns on the Earth. These are the same models that were used to highlight and reveal the impact that humans are having on our climate and predict its negative long-term effects into the 2100s. So what we can do and what we have been doing for, I guess it's over a decade now, is changing things about that climate model to allow us to predict climate and weather patterns on an exoplanet. So we can change the host star, we can change the atmospheric composition, we can change the orbit, we can change the surface type. the orientation of land and ocean and ice. And I use observational data where it's available. And sometimes I create fictional planets and think about whether they could actually exist out in space, which is one of my favorite things to do. So one of the first things that we start off when we're looking for these potentially habitable worlds, the observers find a planet that orbits its star at a particular distance or range of distances that we call the habitable zone. And that's denoted by this blue swath of space, which of course is farther out from hotter, brighter stars than it is from cooler, dimmer stars. In the same way that if you're on a beach, you'd have to stand a lot closer in to a small, teeny little campfire than you would a large bonfire to get the same total amount of heat. So too do we have to be closer to these cooler stars to get the same total amount of energy or heat. Question? I missed the beginning. A little louder, please. Oh, the units. Okay, the question for those on Zoom is someone's wondering about the units on the X and Y axis in this plot. So this is, let's see, on the Y axis, we have stellar mass in solar masses. So here we are as the sun, 1 solar mass. And then here we have about 1/10 of a solar mass, 0.1. And then this on the X-axis, this is what's called a log plot. And this is, let's see, this would be, so I believe this is in astronomical units. And 1 astronomical unit is 1.5 times 10 to the 8th kilometers. But for the purpose here, it's like distance going out as we go this direction. So we here on Earth would be right there, smack in the blue region of our, away from our sun, right in the middle of the habitable zone. Yeah, thank you for asking that question. Another question, yes. Much. No, well, love this. So I'll repeat this again for Zoom audiences. The question is, this plot is showing you only up until a solar mass, only up until the sun, and stars can get a lot hotter and brighter than the sun. It's absolutely true. So what happens after that? Well, let me ask you, what do you think would happen? What do you think would happen to this blue swath? Is it gonna go, or is it gonna keep going, or what do you think? You might be right there. The one thing is, I will say, the hotter and brighter the star, the farther away you're gonna get. Yeah. Right, because there's not an infinite number of types of stars that, yes. Yes, there's also, it gets a little more fine-tuned for the hotter, brighter stars, because, and I'll mention this in a little bit, that the hotter and brighter your star, the quicker the star is going to burn out. So there's temporal qualities to a habitable zone, which would adjust what this plot looks like too. But absolutely, this is very, I would say, solar focused. And generally that's because the habitable zone, we're more concerned with things that are no brighter than the sun, because the lifetimes of the stars are going to affect the lifetimes of any planets around them. And so this is the parameter space in terms of stellar environment that's most important for us who are looking for habitable planets. But you're absolutely true that there are other more brighter stars out there. Yes. Yes, you are all, so question was, the habitable zone is, he's presuming, or what's being presumed is that this is liquid water based, and I'm about to get there. But are there other factors that go into this calculation of the habitable zone? And that's, yeah, that I could do a whole other talk about this. The habitable zone, in essence, is predicated on liquid water. That's what, and we're also assuming that these planets are, that the habitable zone assumes that planets around these stars have Earth-like atmospheres, have carbon cycles that will adjust the silicate weathering rate with temperature. These are all things that we cannot confirm yet on exoplanets. We are very Earth focused when we talk about this habitable zone. Tides are not a factor in this particular habitable zone. In fact, there have been scientists who have proposed a separate tidal habitable zone that should exist. Yes. Yeah, so comment coming in about the other ways to create a habitable zone, including that would account for moons such as Saturn's moon Titan, which if has a liquid, it's not liquid water. So if we found life there, it would be very much life as we do not know it. And I think this is an area we would love to have you contribute to, because we, keep at it. Good. Yes, you had a question.
You're also assuming that the habitable zone is not.
Yes, good point. So comment is that we're assuming the habitable zone, this is about surface liquid water. Yes, and that's why this does not incorporate things like tides, which are responsible for, there's a moon in the solar system that has liquid water, but it's not on the surface. There's a couple of moons actually, but can anyone name one? Yeah, I was thinking of Europa in particular, although yes, Ganymede too. And then Enceladus. Yes, so Europa and Enceladus both have liquid water oceans underneath ice, and Europa's is global. And those are due to the tidal interactions between Europa and Enceladus and their parent planets, right? Jupiter and Saturn. So this is a whole different, because those moons and of course their planets are way outside of this habitable zone. Right? So how do they even have liquid water? It's not about the star. It's not due to proximity to their star. So yes, the habitable zone has its limitations. And in the program that I was in for 5 years here at UW, and in the Virtual Planet Laboratory, Vicki Meadows' group, we talk a lot about this and how the habitable zone, it's an important first step. It is by no means comprehensive, and you've just outlined many exceptions that require this discussion to be much more complex than it has been so far. Great points. Okay, I will continue on. So you've sort of started to do the rest of my talk for me, so which is great. The habitable zone, right? Too close in, the oceans would boil away. Too far away, and the oceans freeze. So again, it's so much more complicated than that. But we are talking about liquid water. That is our main criterion for a habitable environment. It cannot be our only criterion. And of course, there are astrobiologists whose job it is to look at other ways that life might be able to conduct its chemical reactions, other solvents it could use. But we know that all of life on the Earth, from the tiniest microbe to the largest elephant, requires liquid water for chemical bonding and as a solvent for chemical reactions. So it is liquid water that drives the search for life elsewhere. And when it comes to the factors that can affect the long-term presence of liquid water on a planet's surface, it's incredibly complex. And again, when I was here at UW, my primary advisor, Vicki Meadows, hosted a workshop, and we sat in a room for a couple of days and hashed out what are all the different factors that can influence surface liquid water. And this map is now published in her paper with Rory Barnes. And so over the past decade plus, I've been chipping away at various aspects of stellar effects, planetary effects, when it comes to the planets and their host stars that could influence this habitability on the surface of a planet. And it's been really fun. Of course, when there's so many factors that can influence liquid water, you have to stick to a few and try to go as deeply as possible. So I've honed in. I think I would say that surfaces and albedos are really my main factors that I've enjoyed. There's been a lot that I've been able to do over the years since graduating, and I have to say that I probably wouldn't have been able to do any of them were it not for the second chance that I had to have and acquire a PhD here at the University of Washington. So I wanted to share a little bit about my journey, and then I'll share with you some science results that are pretty exciting over the last year or so. So I had this, as Vicki mentioned, I had this dual interest for almost as long as I can remember. I loved astronomy and I loved acting. And I loved like sci-fi movies and shows. And I had this inner conflict. I was like, do I want to be doing what the characters in the shows and movies are doing? Or do I want to be doing what the actors are doing? I wasn't quite sure, but I loved the world that I was being invited to experience when I watched those shows. And so I thought at first that it was about what the characters were doing, exploring the galaxy, exploring uncharted regions, even if it's in the deep ocean, which is basically like space, but on our planet. And so I went right out of undergrad to a PhD program and started that at the University of Wisconsin-Madison. But I was conflicted there. I still had the acting bug. I had done a lot of acting in high school. And I looked around me and no one really looked like me who was in the program with me. They all sort of looked like this. And I thought that meant that I shouldn't be there. I also had a white male professor tell me to consider other career options because I was, my attention, did someone say who? I'm not gonna name names, but yeah, he knows who he is. But I did listen, and that was a choice that I made. It's not a choice I would make today, but I did. I listened and I left. I left that program, and I ended up saying, okay, I'm gonna try that other thing I was interested in, acting. So I went, and because I'm a good student, I can't just do it. I have to study it and get a degree. So I went and got an MFA in acting, and then I did odd jobs and had a few successes. I got into a movie that got me my SAG card, and it was called 9 Lives. It went to Sundance. It was one of Ebert and Roper's top 10 films of 2005. It's a great movie. And I was even in a science TV show that was exciting on PBS. And I thought, like, this is it. I've got the science and the acting. It's all coming together. But that wasn't it either. This is me in a Greek tragedy, saying goodbye to my son who's about to be flung off a cliff, because that's what happens in Greek tragedy. But it wasn't like I kept on thinking about astronomy, and I'd be driving through the streets to some odd audition, and occasionally I'd look up and I'd see like one star through the smog-laden sky, and I ended up taking a day job working for the Spitzer Space Telescope. And that's where Vicki and our paths crossed. And I started to listen to talks, again, astronomy talks. And by this time, it had been almost 10 years since I'd left Wisconsin-Madison. And the field of exoplanets had exploded during that time. And those were the talks that I was drawn to. And so I started that arduous task of applying again to astronomy PhD programs. And I got into the University of Washington. And because they had an astrobiology program, that's why I wanted to be here. They also had a much broader idea of what a graduate student could be. There were people who had been to the Peace Corps, people who had gone to pastry school before coming into grad school. And I thought, I'm not so much of a rare magical unicorn. Like, I'm gonna come here. They took me out for Ethiopian food that when I visited, and I was like, I am definitely coming here. But it was a wonderful experience for me to exchange my life in Hollywood for a life in the Pacific Northwest. So in the Life in the Universe class that I teach at UCI, we talk about what makes the Earth habitable. Because we start off with, how life started on the Earth as far as we know, because again, an area of very active research. We still don't know for sure how you get from organic compounds to life. That's a big gap. But we talk about what we know, and then we talk about how Earth is habitable. Why? What are the chief factors? And then we use that as a springboard to then go out into other planets within our solar system, planets and the moons. Why are they not habitable? Or why might they be habitable? And then after their midterm, we go on to exoplanets. But when we talk about what makes the Earth habitable, an atmosphere comes up first thing. Why is an atmosphere important for life? Well, it comes back to liquid water, right? That all important ingredient for life. An atmosphere allows for liquid water in two ways. If you think about those phase diagrams, the temperature pressure profile, it provides the necessary atmospheric pressure and it keeps the Earth warm. So it got me thinking about habitability and environments. And so I wanted to spend the rest of the talk thinking about what makes a habitable atmosphere for a scientist. And we're going to switch out this little cartoon and make this one instead, right? For this scientist, what makes the atmosphere habitable? What has made my atmosphere habitable? So I've come up with several essential elements to habitability for a scientist. And these are not by any means exhaustive, but the main ones as I see them: communication, collaboration, generosity, and autonomy within the legal bounds. Autonomy, okay? And really what I mean is that, autonomy is the right to choose, as long as we're not harming others, the direction we want to go with our professional and personal careers. So I'm going to start off with communication. During my first year as a grad in the astronomy program and the AB program, so when you're a first year, you can go to what's called journal club, where grad students give talks about other people's papers. And as a first year, the first quarter, you can just sit in and you get a free credit. You don't have to give a talk yourself, which is wonderful, because as first years, you were all like overwhelmed and freaked out of our minds. And then it was our turn. We had to give the next quarter. Had to get on the schedule and give our talk. So I chose Saturn's moon, Iapetus. I loved this moon. It has this dichotomy, and I knew this personal connection I had. Oh my gosh, it's got this bright surface. It's got this dark surface. It's almost a yin-yang appearance. It sort of mirrored this duality I felt with the acting and the astronomy and the science art thing. And so I presented a paper about proposing a theory for the origin of this material and this dual nature of Iapetus. Well, during the first, I think it was like minute of talking, I was interrupted with a question. And the question was, in what direction does Iapetus rotate? And I didn't know. I hadn't the foggiest clue. And instead of saying that, I said, like this? And I was mortified. There was this huge gaping silence that seemed to go on forever. And then all I could do was just go on with the rest of the talk. And then, of course, I kind of collapsed into a pile of tears in the office with my, the 6th and 5th years who I shared an office with. And they assured me that it wasn't as bad as I thought, but that I might want to work on how I presented figures, because I didn't at the time know how to blow them up and still maintain the resolution of the figure and, all this. And that was useful. But what I did do is I reached out to Eric Agol, who's a professor in the astronomy program. And I asked him about this whole Q&A thing, getting questions from an audience, because I had no problem with talking in front of people. I was an actor, I had trained to get up in front of people and say stuff. But what freaked me out was the questions, because I couldn't plan for that. It was this complete X factor. And so I went deer in the headlights when I was asked a question, and I hadn't had time to plan my answer. And what he told me was, you always have a few moments to collect yourself, to hear the question. even if it seems like it goes on forever, it really doesn't. You can take that in. And if you have some information to share it. If you don't, you can say, I haven't thought about that, but I'm happy to look into it and get back to you. It's that simple. He also reminded me that people asking questions, it's a dialogue. It's a good thing when they ask questions. It means that they care about your work. And if you've ever been at a talk where no one asks you any questions, that's far worse, because you don't know if it's that they didn't really pay attention because they were asleep or they want to go to lunch. Like, it's a good thing when people ask questions. So this idea of communication, that just Eric taking that time with me to sort of tell me, hey, here's an idea. It started to make it easier. It wasn't easy right away, but it got easier and easier. And now it's almost like I don't even remember that person who went deer in the headlights. You know, I know that as a person standing in front of people talking, when people ask me questions, you know, there's a tremendous amount of power that I have too. If there's a question that comes totally out of left field, that has nothing to do with what I was talking about, I can always redirect them and say things like, great question, blah, 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 blah. What I want you to focus on is this. These are things I didn't know before I came to grad school. Communication, it allows me to, do things like establish boundaries with co-authors on my papers. I've learned here that saying things like, hey, let's all work in this way. You do this, you do that, I'll do this. Here's the proposed author order, this. Let me know if you have any issues with that, right from out of the gate, rather than as I'm about to submit a paper saying, here's what the author order is going to look like, right? That's effective communication, sharing things as early as possible. I learned how to do that as a result of these kind of early educational experiences with communication. Collaboration. So as a grad student, I was looking for that thing, that light bulb moment that was like, I want to work on that. That thing that was going to get me out of bed every morning to work on it for 5+ years, because I knew it wasn't going to be my advisor. Like that wasn't either of their jobs. I had to find something that I could hook in on. And it happened to be, I wandered into another journal club talk, and a more senior grad student was giving a talk on this paper with a very long title. And I had that moment, that bingo moment. They were talking about how water, ice, and snow has this property where it behaves differently depending on the type of light that comes from the host star, water, ice, and snow on a planet. And that a particular type of star called a red dwarf star emits predominantly in the range of the spectrum where water, ice, and snow really like to absorb. And as such, this could affect the climate of planets around these red dwarf stars. So I got super excited, and I had no idea who the first author was. Never met him in my life, but I cold emailed him. Again, communication. I thought, and my acting background taught me about networking, and I was used to like going into rooms where I didn't know anyone and walking up to someone and saying, hi, my name's Aomawa Shields. What's yours? So I felt a little emboldened, and I reached out to him and I said, are you going to do any more work in this area? This paper wasn't a modeling paper. It was a suppositional paper with a simple scaling argument to back it up, and no modeling had been done. And so I asked if he was planning to do any, and if so, could I be involved? And that led to 2 papers that comprise the bulk of my dissertation. So again, this proactive nature, which I cannot underscore strongly enough for grad students in the room. Like, if you want something, if you're interested in something, don't let that fear of how you might be received hold you back. The worst that he could have said is no, or never replied. So about these stars, and we had this question earlier about the stars that are brighter than the sun. So let's talk about those. So here's a little stellar primer. There's us, our star, the sun, is a G star. And these red or M dwarf stars are over here. They're cooler and smaller, much cooler and smaller than the sun. And they are like the tortoises of the stellar family. Because they're so cool and small, they burn through their fuel very slowly. And as a result, they live for a really long time, hundreds of billions, and in some cases, trillions of years. So no M stars, no red dwarf stars have ever died because their lifetimes are longer than the current age of the universe. So that's a really good thing, given that they comprise about 70% of all stars, are M dwarfs, red dwarfs, and they would offer lengthy timescales for both planetary and biological evolution. So it's one of the reasons why we've always been super excited about the prospects for life on planets orbiting red dwarf or M dwarf stars. Let's see, so the question is, would life exist at Mercury's distance from their sun? It depends on the type of M's or the type of red dwarf star, but a planet in the habitable zone of a red dwarf would be like, well, I guess we could go all the way back to that plot, but would be like, I think I want to say a 1/10 of an AU to like 0.3 AU. So much closer in, yeah. But there's also some potential drawbacks to being that close to your star, which we'll talk about briefly. So at the other end, the O stars, right? These are like the James Dean of the stellar family, or I have to scale it up for my young 20-something undergrads and say like the 27 Club, right? And it's, you know, it's sad. These are all people who died before died at age 27. So they live fast, they die young. Those are the O stars. They're the gas guzzlers. And that's why we don't talk about them very much when it comes to habitability. And that's why the habitable zone plots don't have these stars on them, because these are like half of, millions of years for their lifetimes. And that's not very good, given that it's believed to have taken life on Earth about 500 million to 1 billion years to get started. So we tend to stay in this range. So a lot of my work has focused on the cooler, smaller stars, particularly looking at their starlight and how that light interacts with different surfaces and how that interaction can affect planetary climate and habitability. So I started off as a grad student with this water-ice albedo feedback effect and how we think of water ice on our planet as being a very bright thing. And the more light that ice reflects, the colder the planet gets, more ice forms, temperatures get colder, etc. That's the positive feedback. But ice albedo has this spectral dependence. So this ice albedo feedback mechanism is going to be sensitive to the wavelength of light coming from the host star. Water ice likes to absorb longer, redder wavelength light and reflects shorter, bluer light. And that's why this iceberg looks so blue. Right? The redder light is absorbed on its way through the ice. Only the blue light makes it all the way to the bottom to be reflected back up to our eyes. Then we see blue ice. Okay. I love this photo by Steve Warren, who's here at UW, Professor Emeritus in the Department of Atmospheric Sciences, and one of the first people to really teach me about ice albedos. So you see here two of the end members, this very, very coarse, large-grained blue marine ice, where you see that blue color because everything is, like, there's a lot of absorption happening, very little scattering, and so that light is getting all the way to the bottom, red light getting absorbed on its way through, and infrared light, and the blue light getting reflected back up to us, whereas the finest grained ice, which is snow, you see a lot of that scattering happening, and so we just see white. So thinking about M dwarf planets, we kind of talked about this, and I studied this phenomenon, and thought about how these planets could freeze, and how this ice albedo feedback with spectrum can, the interaction of the host star with the ice can allow these M dwarf planets to be harder to freeze and easier to thaw, because the ice is more absorptive if it's on a planet orbiting an M dwarf, which likes to emit in the infrared part of the spectrum where the ice likes to absorb. So I spent a lot of time thinking about that particular phenomenon. But of course, planets can have a lot more on their surfaces besides ocean and pure water ice. And so after grad school, I was able to continue my interest in surface albedo feedbacks, but expand this beyond pure water ice. So one of the first papers I did after the PhD really was with UWAB grad student and glaciologist in the Department of Atmospheric Sciences, Regina Carnes. And we looked at a different type of, well, it's water ice with precipitated salts in it, essentially sodium chloride dihydrate, also called hydrohalite. So it's really, really salty ice. And that in bare sea ice, that salt can precipitate at low temperatures below like -23 Celsius and crystallize. And that crust can be much, much brighter than regular pure water ice. And I love how this collaboration came about because she called me up and said, I'm looking at this and how it would affect the energy balance of snowball Earth, which is a time in history when our planet was believed to have been covered in ice from pole to pole. And she said, do you want to think about it from a standpoint of snowball exoplanets? And I said, yes. And so we did a paper. I remember finishing it not long after my daughter's born. And there at my daughter's daycare, they actually printed out the paper and put it on the daycare wall and with a picture of her with his glasses. It was just so funny. So I was very proud of that. And I also extended this surface albedo feedback. So this collaboration, again, this was UW-AB program. This was what I was taught to do. The collaboration, remember, we're thinking about that particular element essential to habitability. I took a class that was taught by Vicki on professional development. And what I learned was that you didn't have to be an expert in all aspects of a given study to undertake that study. You didn't have to go get 6 PhDs to be able to write a paper. We could work with others and everyone could bring and lend their own expertise to bear on a single question, in this case, thinking about hydrohalite. And it taught me to be able to explore and pursue those collaborations myself after I left. I was so grateful that, when I went to Vicki and said, this is what I would like to work on for my PhD dissertation, and it was climate modeling, which I think to my knowledge, she had not done very much of herself. She knew someone who had, and she matched me with Professor Cecilia C.C. Bitts in atmospheric sciences, who was a climate modeler of Arctic sea ice. And to my knowledge, she had not lent her expertise with climate modeling to bear on exoplanet questions very much. So we both were learning together. I had a lot more to learn than she did, but she took time to show me how to use climate models. And again, it was like bringing their expertise to bear on shared questions. And I got to learn that that's really what science is all about. It's a team sport. It's not a solo enterprise. So it really helped shape the way that I ended up kind of emerging as a scientist. It also allowed me to be able to lead proposal teams myself, even 10-member multi-institutional teams that were applying for multi-million-dollar grants. And I did that one over the pandemic. I led a team that was the largest team I'd ever led before. We didn't get the grant, but what I learned was immeasurable in terms of delegation and assigning responsibilities, determining how we were going to shape a project, and identifying expertise and who in the country, whose expertise I needed to be able to answer the questions that I had to write a compelling proposal. So I was able to work with a postdoc who I also think I crossed paths with at UW for the first time, or somehow was part of the VPL environment. And then turns out I hired him as a postdoc, and we started to talk about and study land albedo feedback, because of course these planets could have incredibly different and various land surfaces. And we applied some of what we learned to the TRAPPIST-1 system, exploring a range of different land surface compositions and how the stellar effects could, between the host star spectrum, TRAPPIST-1, which was a very ultra cool M star, and potential both bright and dark land surfaces that could be present on the most potentially habitable of the 7 planets. The main punchline of this work really is that the surface matters. And that's important. A lot of observers that I've crossed paths with kind of have the idea of like, we're not going to be able to tell what's on the surface. Let's focus on the atmosphere. And I'm always jumping up and down saying the surface matters. It matters. And we can see the climatic effects when we change surface composition. And yes, it's going to be harder to determine what is on the surface remotely, but it matters, and it has a strong radiative effect when we quantify that with the surface and the stellar spectrum. Okay, so let's move on to generosity. So this, I mean, I've already talked about it to some degree in terms of the way I was mentored, right? How much time both Vicky and Cece devoted to teaching me what I needed to know. That in itself is the definition of scientific generosity. And now that I'm a professor, I recognize how much time that really is, taking that time out to mentor a student, to sit down and teach them how to use a model that they need to use to be able to advance through their dissertation years. Also, not long after I finished, I started to propose for more grants. And Julianne Del Canton, who is not at all in the same area scientifically as I am. She's a galaxy scientist and had at the time one of the largest Hubble programs at that was active, the Pan-Chromatic Hubble Andromeda Treasury, to survey the Andromeda galaxy. I reached out to her about proposal writing, and I had a proposal for the NASA Habitable Worlds program. And I asked her if she would review it and give me feedback, and she tore it apart. And that was excellent because she reminded me that the executive summary, which is that first page that people are going to read, is probably all they're going to read. It's going to be the reason why they put it down on the plane ride to where they review your proposal, or it's going to be why they want to keep reading and do so. So you have about a page and maybe even the first paragraph to convince them to keep reading or to throw it in the wastebasket. And anything else that I wrote was secondary, really. It's all about that first page. And so she helped me immensely to craft that ended up being a winning proposal, really through that first executive summary. And I, in turn, have been happy to lend my expertise to people who are proposing, both postdocs and elsewhere, sharing my successful proposals with them when they were proposing for something that I had been awarded. And I've gotten that in return. People are always happy to share their successful proposals with other people, with me when I've asked. And that is an example of the generosity that I've experienced. And granting credit where credit is due. So like, I'm personally of the opinion that offering someone a co-authorship for some contribution they've made to a paper I'm working on is, it is not something that I think of as like a big thing to offer. It's common courtesy. And why not? Because that's also been offered to me. I also wanted to say that, you know, I have had the pleasure of leading proposals and certainly leading papers. I've also had the pleasure that's been important to me, and for me rather, of not being the lead on papers, of being way down the proposal order. And I think it's been good for me. It's been good for my ego because I'm the child of performers. So, you know, we all like to be in the spotlight. And it's good for me not to be sometimes. I was on this paper by a bunch of observers, and they wanted a few habitability folks to comment on the potential habitability of this planet that had been discovered. So it was like a few paragraphs to comment on what prospects might exist. And, you know, it was nice. It was nice to not be in charge. It was nice to be a worker among workers and to be led. As sometimes I have led. Learning to be part of a team without having to be the leader is good. Yeah, absolutely. And I'm proud to be on an observing paper, discovery paper. Yeah, so, and I've also been on, you know, papers that have been model intercomparison papers where, as my name has been associated with like ice albedo and the person that can sort of calculate the broadband albedo given a certain spectrum for a specific surface type, they asked me, can you calculate some albedos in the for the paper that we're working on, and we'll give you a co-authorship. And sure, you know, and I'm not expecting to be high up on that list, but it's nice to be able to share the important principles around ice and climate, and to see that they're valued and to be part of that effort. And then autonomy. This, again, I define this as empowerment to pursue new research avenues, as I have felt that interest, even if they have taken me farther afield from where I started, and maybe especially so. So like we've been able to look at some types of planetary systems that are unusual compared to the ones we're used to in our own solar system. I'm talking about kind of eccentric planets, planets with very oval-shaped orbits that might take them within this green swath is the habitable zone in this image, within and maybe far outside of the habitable zone, and what this might do for life, where you might have very temperate climates here close to the star, and perhaps the planets freeze over at farthest approach from the star, and what would that do for life? Certainly, this habitable zone again, remember I said it's not all sunshine and rainbows close to a star around an M dwarf. In fact, when you're that close, you could have some interesting things happening, like an extreme case of tidal locking. I learned this here at UW, that this term tidal locking is used synonymously with synchronous rotation, and they are not the same thing. I can thank Rory Barnes for that distinction, okay? I was trained here, I was raised here, that tidal locking means there's some slowing down of a planet's rotation rate as a result of the gravitational effect between the planet and the star. The most extreme case of tidal locking is synchronous rotation. And that's a one-to-one spin-orbit resonance, where it takes the same time for the planet to rotate once on its axis as it does to orbit the star. And I always, in my Life in the Universe class, I actually have a student come up and I prove to them that the planet is rotating. It's rotating so slowly that it's always showing the same side, but it's making a full rotation. So yeah, it's a pet peeve of mine when people say tidal locking and they mean synchronous rotation, because they're not the same thing. All synchronously rotating planets are tidally locked, but not all tidally locked planets are synchronously rotating. Okay, thank you, UW. Thank you, Rory Barnes. So in this configuration, I thought to myself one day, could you have a planet that's too hot on the day side and too cold on the night side, but just right along the terminator, the dividing line between? And this is one of those, like, inventing a fictitious planet and seeing if its climate could be stable using climate models. And it turns out you can't. So my postdoc, Anna Lobo, was able to show that this, we call it terminator habitability, Arnold Schwarzenegger reference aside, that it's hard to make a planet have this climate where it's only habitable along the terminator if the planet is covered in ocean. It's especially hard. You either have an entire hot planet that loses all of its water inventory to space, or you have a planet that totally freezes and gets night side cold trapped. But if the planet is a land planet, meaning that primarily you're only having water in the atmosphere, water vapor, but nothing really on the land, on the surface, you can have this terminator habitability state, and it can be stable. And it could be that M dwarf planets are more water limited. They start off in general with less water inventory given their smaller sizes and their smaller protostellar nebula. We've also looked at this not just for M stars, the M star stellar environment, but for a little brighter K dwarf stars too. And we've compared this terminator habitability regime and scenario. So for the M dwarfs, right, we see that you've got this water vapor escape, either water vapor escape or night side cold trapping if you're an aquaplanet. But if you're a land planet, you can't have the terminator habitable planet. With K dwarfs, you end up having more likely you're going to have an eyeball situation than a terminator habitable situation. So an eyeball is when you have like an open area of ocean right under the substellar point, and the rest of the planet is frozen. But you're less likely to have this terminator habitable scenario, which I can elaborate more on if you have questions, or there's a little QR code to read the whole paper. I have a grad student who's, again, thought about this eccentric planets and how you may not just have water ice on their surfaces. You could get so far out at farthest approach that other forms of ice form on the surface, like CO2 ice. Perhaps the eccentric planets go through these periods where they're freezing to form water ice, then they freeze, and then the CO2 actually condenses out of the atmosphere to form ice. And CO2 ice has a very different albedo situation and spectrum than water ice. And her work made the front page of the journal Astrobiology in January. And she designed the cover with her little Adobe program. She designed a really great cover. So that's her QR code to go to her paper. And finally, I was able to return to my own kind of first authored work recently, and it took a while. It took me about 3.5 years because I wrote the book in the middle of it. But I eventually got this paper out, and I felt proud of that. Looking at white dwarf planets. So a white dwarf is the end stage of our sun, and most of the stars in our galaxy will become white dwarfs, where their nuclear furnaces will expire and they'll become dying embers over time. So I'm going to show you where we did a study of 2 planets, and one was a planet around a K star, so those orange stars, a little bit cooler than the sun. And then the white dwarf we picked with a similar temperature. So what you're seeing here is where the habitable zone would be of a planet around that K star. So here's that blue swath, here's where it would be. And then the white dwarf star would be similar effective temperature. So, but given that it's a tiny little dying ember, guess where its habitable zone would be? Super close. It would have to be super close because it's so dim. So we compared, and this is what a lot of my output from climate models looks like. It's essentially like if you're unfurling a globe and making it flat. So you've got latitude here on this axis, longitude here on this axis. And this is surface temperature. And this is the planet around the K star, the orange star. Its orbital period is 155 days. This is the planet, same around a white dwarf of a similar effective temperature, but look at its orbital period. That's 10 hours. So because it's so close to its star, it is whipping around. They're both synchronous, so they both have that one day side, one eternal night side. But you see, another team has called this configuration or this pattern a bat rotator regime. And I guess you can see why that is. But what's interesting is that the temperatures here on the white dwarf planet are much warmer. And there's a couple reasons for that. That fast rotation is stretching out and elongating the scale of atmospheric circulation. So there's not a lot of clouds that can form, that are able to form on the day side in the white dwarf planet's case. Compared to the K dwarf planet, we've got that big, thick cloud layer, liquid water cloud on the day side, which can cool things down significantly, reflecting light back to space. But for the white dwarf, you see that stretched out scale. If I show it to you in a different pattern or a different dimension, a 2D plot here of liquid water cloud depth path as a function of latitude, you see this is the day side. Super, super high amount of cloud on the K dwarf, which happens to be Kepler 62. So this is a planet that is orbiting a hypothetical planet orbiting K62. There are actual planets that were found around Kepler 62, but these are hypothetical planets between a couple of the orbits of Kepler 62. And you can see there's a lot more clouds on the K dwarf than the white dwarf. So that also allows this white dwarf planet to retain a lot of its heat. It also transports a lot of heat equatorward from higher latitudes. So I wanted to show you the power of this climate modeling because, yes, we don't know yet if white dwarf planets, rocky white dwarf planets, exist. It could be that the tumultuous phase that gives rise to the white dwarf obliterates any prospects for planets around these, but we have found giant planets around white dwarfs, and we found debris disks around white dwarfs. And so the prospects are getting, are increasing for us to be able to find rocky planets around white dwarfs too. And autonomy has also led me to veer off the beaten path a little bit compared to what I have seen in academia. There's a culture of productivity and work and doing a lot. And I found that not to work so well for me, both physically, emotionally, and mentally. And so I discovered something called Yoga Nidra about 2 years ago now, I guess, and became certified in how to do this. So I offered this workshop at UCI for the first time last fall. And instead of teaching astronomy classes, I taught rest. And we had faculty, students, and grad students and staff enroll. And we had Zoom and in-person workshops over a 10-week period. And people found them incredibly helpful. And in many cases, they didn't realize how exhausted they were until they lied down to rest. So what is Yoga Nidra? Well, it's a sleep-based guided meditation that's carried out lying down. And what are its benefits? There's a number of benefits, including reducing anxiety and improving sleep quality. And to give you some evidence, it's actually been used in partnership between the Walter Reed Army Medical Center and the Department of Defense to treat soldiers suffering from PTSD. So it's got to work for college faculty. But I think what really sealed the deal for me was when I read in a book that 30 minutes of Yoga Nidra feels like 3 hours of sleep in your body. And I thought, sign me up. I'm a mother of a young child, like I'm exhausted. So I've offered some Yoga Nidra workshops at other academic institutions since the UCI one at Princeton in February that was oversubscribed, and then one at Caltech. This is a little picture I'm taking of I took while I was conducting the workshop. So this literally could be you right there. And I'm happy to provide resources to anyone who would like to know more. There's great apps that have meditations you can listen to. I also have developed an appreciation for that elusive work-life balance that people always talk about, that I've tried to be more intentional about carving that out and talking more about it so that the younger generation can know that it is possible. If they want to continue in academia, they can do so and have lives. They need not wear their busyness as a badge of honor. And I'm trying not to do that myself and to talk more about not working rather than feeling guilty about that. So there's a book that Vicki mentioned that I'd love for you to read if you'd like to know more about my story. The main thing is that this is one way to look for life elsewhere, but it's not the only way. And of course, we're getting closer and closer. My hope is that we will definitively answer that question, are we alone? If not in my lifetime, then in the lifetimes of some of the younger folks in the audience. And lastly, I want to mention Rising Star Girls. I'm finishing. Rising Star Girls is a program that I founded, and it really started in many ways here at UW as well. I was giving planetarium shows to middle school girls of color from different schools around the city in Seattle. And then I thought about this for a postdoc fellowship application. Like, there's got to be a way to put theater background I have and astronomy together. And I found in the literature that there was precedent for it, that when you incorporate creative arts activities into astronomy education, you increase girls' confidence in both asking and answering questions. So that started this whole process for me of creating this program. And we're in our 10th year now. Just as if, I knew I was told you I'd come back to the Milky Way and how there's stuff behind these dark patches. It doesn't mean there's nothing there. If we looked at the Milky Way in one particular form of light, visible in this case, we'd miss out on so much information compared to looking at other forms of light, like infrared in this case. So too is there so much more to these girls than meets the eye. And we want them to know that their personal backgrounds are essential to their study and practice of astronomy, that they need not hold their personal backgrounds to the side and pretend that whatever's gone on in their home that morning is something that they cannot bring into what they're learning about. We want them to write poems to incorporate their stories and their backgrounds so that when they look up at the sky and the stars, they can say, I wrote a poem about that nebula, that planet, and claim ownership of that. And the hope is that if they have that personal connection, they'll be less likely to turn away from astronomy as they continue and the heavy math and physics enter the picture. So they do things like create their own artists' concepts of actual NASA remote sensing images. They design their own exoplanet environments, like we did that visualization at the beginning of the talk tonight. They make choices about whether there's life on that planet. If not, why not? If the life is there, what kind of life? What's the sun like? What's the landscape like? During COVID, we moved to virtual and we continue to offer summer 2-week virtual workshops. And we are now funded by the Heising-Simons Foundation, and that's allowing us to be able to move back to destination workshops. We were scheduled to go to South Africa this year to work with girls, and unfortunately we've had to cancel that trip due to the current political climate and visa concerns for some of my international student facilitators, but we hope to be able to do that one day. So the girls are always learning about, of course, the basics of astronomy, but they're doing it through this creative arts lens. And I'm proud to be able to say for the first time, we actually have a peer-reviewed journal article on the efficacy of our approach. And so we've got one of my grad students spearheaded the paper, and this covers over a decade of workshops that we've conducted both in person on both coasts and in virtual. And these terms, Higgs gain and effect size, really are parameterizations for the change in response before and after each workshop. So we build in assessment metrics both before and after the workshop. And there's the QR code too for that if you want to read more about our full paper. And our website, we'd love to have people involved. We love having people from, especially students, because you're closer to their age than I am, so they can relate more to you. Learning, sharing their own paths and experiences, especially struggling with STEM. For you to share that with them is great, because they learn that science is not always a smooth journey, but they can persevere like you have. And I'm really excited about our new program administrator, Kayla Corona, who's also a military police Army sergeant. So she gets stuff done. And it's been great to have her. So a few parting words to the younger people in the audience or the older people who are starting and they need to have some new paths forward. Learn about yourself. Love what you discover. And I was someone who did this a lot later than I would have liked to, but it's never too late. Develop your own values and trust them. This used to be my mascot, and it didn't serve me very well. And then I thought that it needed to be this, the turtle, right? Slow and steady. But I realized that was somewhat unrealistic for me too. So I think I'm moving forward into this. This is the hummingbird. The hummingbird, as you know, right, 60 flaps per second, right? They're very fast moving, but they rest. And a number of hummingbirds I have noticed outside of my window. We have a tree and a hummingbird feeders, and they visit a lot. And I see how much they are in rest too. And then they go into flight and they, flurry around, and then they stop and they rest. So I'm learning to do that more and more in my life. I think with the path I've chosen, both in academia and outside of academia, there's a lot that's always going to be around and to do. But as long as I build in those times to rest and replenish, I think it can be sustainable. At least I'm planning and hoping for that. and will move me away from doing that, like I often did in those early years as a faculty member, to doing more of that. And maybe even that, like, wouldn't that be amazing? Right? So as we end, I invite you to take one more close of the eyes, and we'll wrap up what you've heard tonight, and allow it to settle in your body. And for a moment, identify one thing that you could take with you that might serve you in some way. And then anything else that didn't serve you, you can leave that here in the auditorium. And leave today as light as you possibly can be. There's a lot going on in the world. Almost every day there's new information, and it can be really easy to feel heavy and weighted down by it all. So let's try to hold on to what we know to be true and what we need to take care of ourselves, whatever that is. Let's take one more full deep breath in through the nose and sigh it out through the mouth. Gently wiggle your fingers and toes. And when you're ready, you can open your eyes. I'd like to thank the UW Astrobiology program for so much. And my institution and funding organizations and collaborators and all of you for your attention. Thank you.
I can bring the mic around for questions.
Hi, I got 3 questions, you don't mind. Can you go back to the habitable zone plot? So yeah, I don't work in astronomy, so this is my first time seeing it. I thought it was very interesting. Yeah, so I know the width is probably distorted because you're on the log scale on the x-axis, but is that width the same throughout the entire plot? Also, why is there a shoulder on that plot? And also, I'm just interested in how these plots are calculated.
Yeah, I mean, it's not like a, I mean, these are great questions. I've gotten this question before, and it's not a straight line. It's not a linear relationship. There is an equation, and this habitable zone was defined by Jim Casting, and then refined by Ravi Kapurapu and others. And there's a lot of factors involved. Of course, the luminosity of the star, and then it's also dependent on, because this is a model. The habitable zone has been modeled for these different stars, the region. And so I think what was used originally to calculate this was a one-dimensional radiative transfer code, which in itself has its own limitations, but it's got radiative transfer and the various absorption coefficients and correlated K coefficients. This is a bunch of technical stuff that just to tell you that there's a lot, it's a long equation that is not a linear y equals mx plus b plot. So that's why it's not just going. So I think that's the most detailed I want to get for this audience, but I'm happy to talk more about that offline if you'd like.
Okay, thank you.
Make my way over there.
Thank you. This was a very interesting talk, and I remember I've been to these for a long time and haven't been to one for a while, for like since I was like 8 years old or something like that. So this is really great. I do a lot of like world building projects with like science fiction and fantasy for creative purposes, and I was really inspired by your methods for creating hypothetical worlds. And so I was wondering if there were any sort of scenarios that you thought should be explored more, because I think that creative works can have a pretty big impact on science. And so I was wondering if there were any sort of types of planets that you might like to see sort of explored more in those ways.
Yeah. Exciting. Well, as you were talking, I thought about, I've gotten a question recently about the forms of life we could encounter. And I don't know if you have watched old episodes of Star Trek, but there was this episode where it was like a silicon-based life form. It was like a big pile of rocks. And I think that it's exciting to think about other ways beyond liquid water that life could use, other backbones besides carbon that life could have in its DNA, and the resulting planetary environments that would support that life. I've been on some History Channel shows where they think about weird planets, and they talk about this environment. You know, there was a planet a while ago that I think that was popularized in the media because it would be like a diamond planet or something like that because of all of the carbon that was there. So I think it really is, the sky is not the limit in terms of what we could imagine there. I think as long as, like with the Terminator Habitable Planet, I started with a basic principle of, hey, this planet around this star would probably exist in this kind of rotational state. Could we have this happen, but not this happen, or only this happened here? And so I think if it doesn't take much to think about some weird scenarios, if you start with some basic principles and you hold fast to the basic science principles. And maybe you don't. I mean, I remember when I watched Avatar, you know, and like we were like, can you have a planet that's floating up and where the mountains are floating in the air? I mean, that doesn't seem very physical, you know. It's like, so sometimes there are things in films that really would not pass the science test, or that would be on Phil Platt's, you know, bad astronomy website. But I think I like it when there's a threshold of science that's strong there, and then you kind of go with, and you have that creative inspiration beyond that. Take that artistic license.
Thank you. Thanks.
Hi. I am an artist who has recently transitioned to being a grad student here in the SEFS department. And so I spent 18 years working in the arts. And I was wondering if you have any suggestions for how to keep your head up when it gets hard.
Thank you. And I realize I haven't been repeating the question for the Zoom audience, so I'll do that here. As an artist, and you said you transitioned to science, or you're in art still?
I have a Bachelor of Fine Arts and I'm getting a Master's of Science now.
Okay.
I was an
Bachelor
animator.
of Fine Arts, doing Master's in Science, and looking for sort of suggestions, guidance for when it gets hard. Oh, yes, read my book. The book is basically all about that, because I did all the don'ts. I did it all the wrong way, and then I did it the right way, and that was here. I mean, there were so many resources here. Even beyond my department, there was a department or a program for women who were re-entering grad school after a significant time away. And I was like, yep, that's me. And they had support there. And there was a woman, Nancy Finelli. I don't know if she's still here, but I mean, she put in the time to check on me, and we had a relationship even past that first year, you know, over email, and met for coffee. And there was a process group for graduate women of color. It was out of the mental health center. And we were from all different departments. And this man, a therapist, Dr. Michael Kane, Black man, made a space for us to meet every Friday. And we would just sit and he'd bring food and we would talk about the trials and tribulations of being mostly Black women in our respective graduate programs. It was a safe space where we could talk about the pressures we were under, and he would help us really find out what we wanted rather than what we thought we were supposed to do. Well, we all had big shoulds hanging over our heads, and he kept telling us, you know, like, what do you want? What's the choice that's going to be indicative of the most love for yourself? And it was amazing how hard it was to answer that question, you know, but because he kept asking that question, I started asking myself that question. So I think finding a safe space, people that you can cry to when it's hard, and they're not going to hold you, or they're not going to use it against you later. They're not going to tell you when you're happy later, well, you were so upset before, you know, they're just going to know that it's part of it, part of the process. And really the resources. So like there was a minority program it had an acronym, Minorities Striving and Pursuing Higher Degrees of Success in Earth System Science. It was MS PhDs, and I found out about it while I was here, and it was run by Dr. Ashanti Johnson, who was the first Black woman to get a PhD in chemical oceanography. And she created this program, and it was like a 3-phase program. And they let me in, even though I was an astronomer, I was like close enough to Earth System Science that with my climate modeling stuff. And it was amazing because I went from being the only one, you know, in my cohort in most conference and workshops to being among 29 other Black and brown students. And we were the majority, you know, and if a white person had walked into the room, they would have been the minority. And we went to conferences together, and the feeling, I didn't realize how isolated I was until I wasn't, you know. So this is not going to be the same. It might be a different landscape for you in terms of what you need, but the point is determine what you need and go for it, because the resources are there. And if they're not here, they're somewhere else. They might be online. They might be in unlikely places. But I think the worst thing that I did was isolate the first time around when things got hard. And the best thing I did was like preempt that by going after every single support system structure I could. And it really benefited me, so that when things got hard, I had that structure to hold me up. Because it's true, like even if you're very well adjusted and you feel like, I got this thing down, there's gonna be highs and lows. As a TA, as with research, courses, you know, and when I was at Spitzer, I had a colleague there, Kartik Sheth, who's now, I think, a head of Alma now or something like that. But he said, you know, have it's like a 3-legged stool, and you've got coursework, teaching, research, and at any given moment, one of those things is going to suck. So you need to have something else to hold it up, or else the stool is going to fall over. And so you reinforce that stool with a personal life. So have hobbies, have things outside, you know, have a life out there, because this is finite. The time you're here, it's 5, 6, maybe 7 years, and then you're on with your life. So don't make it all of your life. Like I took a little arts class at Pratt one quarter. And it was like this art journaling class. And it was like nothing I was doing in my grad program. And that was why I took it. And it was wonderful, you know, and I met people, and like, you know, I had my best friend from prep school lived here. And so sometimes she and I would knit in Waterford, is that the area? Wallingford, thank you. And Wallingford, and like these little nooks inside indoor malls, and we'd knit and then go have lunch or something. And so something find for yourself that has nothing to do with school, so that when there's a low, you've got something else to hold you up.
Thank you.
Still on Zoom because it went dark. Okay, good.
I just want to thank you for the meditation before the talk. I've never been to a scientific talk, or any talk for that matter, except for meditation class. where there was a little meditation first. And it really helped to, at least for me, it helped me to listen without thinking about all these other questions or whatever else is going on that I might have. But it really helped to focus. So thank you for that. Now I have a question about, you showed us a little spectrum of K2 18b or whatever it's called.
Yeah.
Could you show that again? Because I haven't seen it, haven't had a chance to see it before. And
this is the one that's been
yeah, the new exciting stuff.
publicized on, I think I got this from the Planetary Society article. So it's
So there's a
probably.
part that's highlighted that is the sulfur dioxide or whatever it is, dimethyl sulfide. So to me, that just looks like, I don't see a peak. It looks like there's a whole bunch of stuff that could be there that makes up that little slope. Do you have anything to say about it?
Yeah, I highlighted where it might be, the resolution is pretty low in this plot. If I could change something about this plot, I would stretch it out so we could see much more closely, like between the, 3.5 and 4 microns. I'd want to see that because I see what looks like some troughs, but and anyone who's an observer who knows more spectroscopy about this than I can, then please feel free to type in. But if it were me, I'd want to stretch that so I could see, because I bet there's whatever the features are, they'd be more apparent if we could get in closer. So, but yeah, as I said, and EL has been heavily working on this too and scrutinizing it, and that's why it's heavily under scrutiny.
Megan has just handed me the mic here. This is something I've worked on a little bit. But both there was an earlier paper that claimed this DMS, and then the recent claim last week, and both are heavily contested. There was actually a paper that popped up on the archive this week, just claiming that the detection last week wasn't statistically significant. So a lot of people are very skeptical. So I think your intuition that this looks kind of marginal is consistent with the science.
I have a quick comment and then 2 questions. Actually, for that guy over there who mentioned world building, I just wanted to say I also got an Astrobio because of world building and writing, and I actually have a bunch of resources on hypothetical stuff if you want a list for inspiration. So just But anyway, questions for you. Yeah. So questions for you. 1, are you teaching any classes in this upcoming quarter or 2? And 2, what is your favorite dinosaur? I ask everyone this because I feel like everyone knows what it is as a kid, and then they're never asked it again as an adult. So everyone forgets. When I was a kid, I thought which dinosaur was my favorite was the most important thing about me.
So the question for the Zoom audience is, am I teaching any courses coming up, and what is my favorite dinosaur? I'm teaching a course right now, and it's Life in the Universe. It's P20E, which is an undergrad gen ed course, and it's one of my favorite courses to teach. So some of the beginning slides that I showed you tonight are slides that I show as part of that class, and we have a lot of fun. And then I also teach a grad class on science communication, so how to write a paper, how to talk about your science to a broad range of audiences, from traditional colloquium style talks to broader public talks. And then I also teach a grad class on planets, planetary climate. Those tend to be the courses that I teach. I have also taught an energy and the environment class, and I've taught intro math methods physics class. But I can do it if I'm back into a corner. And the dinosaur question. I flashed onto Jurassic Park when you said that, because I thought about what, I mean, I think I like the brontosaurs, because they're large and you would think they would be carnivorous and ferocious, but they eat plants, and I love that. Yeah, so I'm gonna stick with the brontosaurs.
Yeah, the sauropods are really fun.
Yeah.
We have time for maybe one or two more questions. Yeah.
Well, I would love Habitable Worlds Observatory to, yes, the question is, do I have any favorite telescopes that are coming up online that would help in my effort, or help us to identify that, that next planet in the universe where life exists? I think what we need is something, and this was identified in the decadal survey, or I think it was Pathways to Astronomy into the 2020s, is something that's maybe 4 to 6 meter class mirror that will allow us the collecting area we need to be able to identify atmospheric constituents of a rocky terrestrial planet, and look for what we call biosignatures, which is the biologically generated global impacts to a planet's atmosphere or surface that we can observe remotely, like from space. And it needs to be big. It needs to be bigger than Hubble, even bigger than James Webb. And so there have been mission concepts like the Large UV Optical Infrared Surveyor, LUVOIR was one of them. Habitable Exoplanet Observatory, HabEx, was one of them. And I think what was identified was something in the middle. And that's what I'm hoping that we'll see over the next 5 to 10 years.
Okay. Any other questions? I don't see. Okay, great. Then can we give one more round of applause to our speakers?